sorry, we got code language going on. So, our lesson today is these three things, or this right here, the big topic is rational functions. So, what does rational mean, Maddie?
I wrote this down.
You wrote it down. You don't remember yet off the top of the head. That's okay. Go ahead and look it up.
Rational numbers are, they're fractions.
That means there's fractions involved, right? So if it's a rational function, what are you going to see on every problem? Fractions, okay? And so we'll define rational functions here in a minute. Then after rational functions, we're going to talk about different really important types that are asymptotes is the main point of the lesson today. We've got horizontal, vertical, and slant asymptotes are the three different types of asymptotes. So we're going to review what they are. And so let's get started, okay? So first let's start with the fraction part. Rational functions. So the key with a rational function is that it has to actually be, and I'm going to start with the very basic rational function, the very elementary, small, easiest rational function you can write is that. So the key is the variable is in the denominator. Okay? If that's just x divided by 2, it's not rational. It's rational because the x is in the denominator. Okay? Rational function means that your x's are in the denominator. So they're not actually polynomials, they're rational functions. Okay? Do you guys know what that graph looks like? Or what do you know about that graph, just off the top of your head? Is there any problems that this can create? Is there any special numbers that you have to watch out for because of the x in the denominator? Hallie? What's wrong with 0?
You can't divide by 0.
You cannot divide by 0, right? So we have to make sure we go, oh, x cannot equal 0 because why? Never divide by 0, period, right? So you always have to check rational functions for their domain. So can we not be scared of this question? What is the domain of this function? What does the domain mean? All the values that work for x, right? So what's the domain of this function? Everything except 0, which we usually say what? What's the technical way we should say it? All real numbers except 0. X cannot equal 0, right? Remember how we wrote that in interval notation too? Negative infinity to 0, and then 0 to infinity. Does that look familiar to those that took college algebra last semester? That also means all real numbers except 0, because it's open parenthesis at 0, 0, so it's an interval notation, so don't forget that notation, okay? And so that's another way to say all real numbers. Okay? So, yes, Ethan?
With the interval notation, wouldn't it be a closed bracket?
It would not be closed, because if you close it, that means include 0.
Okay.
Do we want to include 0? No, that's why it's open, because if it was a closed bracket there, we might as well just say negative infinity to positive infinity. The open parenthesis means don't count 0. And that's why we break it right on 0. You okay there? Good question. All right, so let's do this function here next. What's going to change on this function? What would you guys suspect on that one, Lorian? What would you expect? We have, oh, go ahead. What would the domain be? When do we get in trouble on this function? So x can equal negative 2. And these ones are simple enough, you can kind of do it in your head, but what did we really do here? We take the denominator and do what with it? Set it equal to 0, right? And then just solve it. And it's really simple algebra, I know it is right there. It gets more complex later. But it's just really set it equal to 0 and solve. That's kind of been the theme of this whole chapter, hasn't it? Set it equal and solve, set it equal and solve to 0. And so here we go. So that gives us our limit on our domain, because that cannot equal 0, right? And so our domain is all real numbers except for negative 2 again. So you got it right on, that's all you have to look at. Okay? Any questions with domain? So domain points out where we have problems, right? Where we cannot use that x value. Okay? So, let's go ahead and roll into our different talks here. Our asymptotes. Can you guys let's start with vertical asymptotes. Let's do it right here. So vertical asymptotes. Vertical asymptotes, they cannot ever be used. So if you have a vertical asymptote, it means that x value can never be used. Okay? Do you guys know what a vertical asymptote, what an asymptote means? Just the general idea of an asymptote? Let's graph it and let's kind of explore that. Would you do the 1 over x, would you? Graph 1 over x on your calculators. And I want you to look for, what do you think a vertical asymptote looks like on a graph? What is a vertical asymptote? What does the word asymptote mean? So everybody got a graph yet? All right, what do you see? What does this graph look like? We're going to do this graph right here, right? 1 over x. And what does it look like? What does the graph look like, Randy?
There's a curved line going below it and a curved line above it.
Like that, kind of? And like this, kind of? And that's just an eyeball test, right? That's not specific points, but it's something kind of like that. So where would a vertical asymptote be located? Anyone got a guess? Oscar? At x equals 0, right here? Oh, that's the same color. Let's not do that. Whoops. Let's do this one here. At x equals 0. What happens to the graph as it gets close to that line? Well, it splits, but what's particular happening? How long, if it's got an arrowhead, what does that mean about how long it keeps going this way? Forever. And is it always getting closer? Yes, and always getting closer. But does it ever reach this line? No, it doesn't, does it? And that would be the vertical asymptote at x equals 0. Okay, and I like to abbreviate that VA for vertical asymptote, just because I like to not write the full words, takes too long. And so that's what a vertical asymptote looks like. Okay? What do you notice about that vertical asymptote and the domain? What's that? They match. So is there a difference in how we calculate the domain and vertical asymptotes? Okay, there is another exception that we'll cover in a minute, okay? But right now with vertical asymptotes, it's really the same process, right? So where would you expect a vertical asymptote with this function? Because the domain is at no, you cannot use -2, right? Remember how vertical asymptotes means you can't have a value there? And so that's what is going to be true. So go ahead and graph 1 over x plus 2 and see if our assumption that the x cannot equal -2 represents our vertical asymptote. Does it shift it over to -2? So see how that just moved that graph over? And so the idea here is domain and vertical asymptotes really are the same. It's just when can we not divide by 0? It's like what values will make it so I divide by 0? That's the problem with domain, right? And that's the problem with vertical asymptote. Now just to kind of a side note, is there other issues besides divide by 0 we have to watch for in our domains? Remember square roots of negatives? We aren't really dealing with square roots of negatives today, but don't forget domain also includes those. Because when would it actually give me a square root of a negative number and things like that? It's not only divide by 0. Vertical asymptotes is only when it divides by 0. Is everybody okay with that? So that's the difference between them. Okay? And it gives us just like x equals whatever that number is, whatever causes it to go to 0. Okay? Let's do this one now. What is the domain of f of x equals x plus 1 over x squared plus 5x plus 6? So what would be the domain of that function? So Lexi, what do you think we should do?
I have no idea.
Okay, we're still working on that.
Yeah.
Ethan wants to help you, so.
Factor the bottom.
We want to factor the bottom, and what's the intent of factoring the bottom for? Why do we want to do that? You're right, but why? Good, so we can get what?
0.
So we can get what makes it go to 0, right? So I'm going to write that first. The first idea is, ready Lexi? what makes my division by 0? So we're going to say, when is that equals 0? Because that's the problem. That's what we cannot do, right? We good with that? And then he said, let's do it by factoring, right? Which is good, Ethan. I know you guys can factor this quick, so let's just get it done. And so that means x plus 2 equals 0, and x plus 3 equals 0. Don't get lazy and not show work, because as they get more complex, you have to have the work, okay? And so then x equals negative 2, and x equals negative 3. We good there? So what's my domain then? All real numbers except? So all real numbers, I'll just use this symbol right here, except x cannot equal negative 2 and negative 3. Okay? So let's go ahead and let's try again. Let's do this vertical asymptote test. What are we expecting for our vertical asymptotes? That it should be x equals negative 2 and x equals negative 3. Plug it in your graph and see if that works. Is there a vertical asymptote there? They're kind of spread out a little bit. You might be better if you change your window to like negative 20 and positive 20. Or actually mostly positive 20, because it's a little bit tall of a graph. You might see it better. So it looks like this. It looks kind of crazy though, doesn't it? What does it look like? Go negative 1, 2, right? There's a vertical asymptote there. Negative 3, there's a vertical asymptote there. And then it looks like this, doesn't it? Doesn't this one kind of come like that? And this one come like this? Is that accurate? And then up here, there's a little thing that goes like that. Is that kind of what it looks like? That's a rough sketch, right? We haven't got exact coordinates on there, so it's not the exact graph. You could look at your values on your table if you needed to, right? But that's just the general idea. But see how it creates multiple asymptotes? Okay? You okay with that, Lexi?
Yeah.
Sweet. All right. So let's go ahead and try this one. Here's the exception. So I'm going to use a different color here now. We're going to go black. We've got the one dark horse here. The one thing that you've got to be careful of that makes you get these wrong. Okay? And it's called, let's just give you the equation. Let's do this one really quick. F of x equals x plus 1 over x squared plus 3x plus, I just did that wrong. Hold on. Oh no, I did it right. That's right. I almost remembered the wrong equation. So let's try that one out. X squared plus 3x plus 2. So what would we expect for the 0? So Haley, can you help me? What would we do to find the domain, the things that are the problems? Factor the bottom and solve it, right? Good. So factor it, which would be x plus 2 and x plus 1. What makes those go to 0? Well, I think you guys already have that finished, don't you? What are they? Sierra, what would make these go to 0? You already have them done? Perfect. So x equals negative 2, x equals negative 1. So what are we expecting for our vertical asymptotes? X equals negative 2 and x equals negative 1, right? Now graph it and tell me if you can see the problem. You already got it graphed? Okay, you already found the problem? And so we're going to talk about how to determine this, right? What's the problem here? There's only one? What does this graph look like? I have one at negative 2, right? That's correct, right?
Yeah.
And then it goes like this, right? Is that correct? Am I remembering it right? Yeah. And there's only one vertical asymptote. Where'd the other one go? All right, so this is the one thing you've got to be careful of. Oscar's got an idea. Where'd it go?
Like it's divided by the top.
Okay, remember we factored this, right? This is actually what? What's the numerator of this fraction? What's the denominator factored to? What do you notice about the numerator and the denominator? If a factor can cancel from the numerator, it is no longer a vertical asymptote. It is called a pole. Make sure you get this separate, okay? So the domain will tell us about, it does tell us values that cannot be used with x, okay? We still cannot use x equals -1. -1 is still out of the domain, okay? Because it's in our original equation, okay? But it divides out, so it's not actually an asymptote, it actually is a whole. So can you guys now graph the function? If we divide this out, what's left? 1 over x plus 2, right? Can you guys graph 1 over x plus 2 on your calculators? Is it still in there? Because we did that already, right? Do they look the same on the calculator? They do, don't they? So it really is this graph, but the x plus 1 and the x plus 1 make what happened to that graph. And you can't see it on your graph, but you can find it there. So what does it mean? Well, we go over to x equals -1, right? Which is right here. And we're actually going to create a whole. So it jumps over that point, because we cannot plug in -1 because it gives us 0 divided by 0, which is undefined. Is everybody okay there? Matisse, how you doing on that? Okay, so how do you tell the difference between a whole and a vertical asymptote? You have to factor the numerator and the denominator and look to see if any factors cancel out. If they cancel out, it is a whole. If they don't cancel out, it is a vertical asymptote. Okay? All right. Any questions or comments anyone wants to make on that? All right, and we are going to move on. So it doesn't change our domain though, right? The domain is all real numbers except for -2 and cannot use -1, right? But now this one, -1 is a whole and a vertical asymptote is there. So let's actually make sure we write the answer down final. The vertical asymptote would be x equals -2, and there would be a whole at x equals -1. It's okay to say a whole at x equals -1, even though it's a line, because it is linear. It doesn't matter how far away from the axis it is. So it's the x value cannot equal -1, and so therefore there's a whole instead of an asymptote. Okay? And it just means you're going like this. You hit it, you jump over it, and you keep going. Okay? And so that's the difference between this graph, which we did, right, and this graph. So how can you find that on a calculator? Because you can't see that, right? It just looked like the solid line. So has anybody got an idea of how we could check on the calculator?
On the table.
Hit second table and look at x equals -1. What does it say? Only on the -1 though, right? -2. Why is -2? So if you can't see an asymptote there, but it's an error, what does it mean? It's a whole. Yeah, and if you do the trace function, you will, yep. And if you're just arrowing over, though, sometimes it might skip the whole numbers, so you gotta be careful. If it's fractional, it's a little harder to tell. Like if it's at 1/3, you may not get that one on your table, right? And it may be hard to know that the trace function if it hit 1/3 or not. And that's why you still want to make sure you always check with the factoring and reducing out. Does that make sense? Okay, you good there, Kyler? Any questions there? Because we're going to move on to the next asymptote if we've got this one here. So vertical asymptotes and wholes. They're all found by setting the denominator equal to, here's our review, set the denominator equal to 0. And then solve. Set the denominator equal to 0 and solve. That's the key, right? And in those values, you have to also look for dividing out factors. If the factors divide out, then it is a whole. If they don't divide out, then it's an asymptote. Okay? Let's go ahead and go to the next one. So we're going to go to horizontal asymptotes. And I'm going to cover the next two in one segment, okay? Because I like you to see the whole picture of this. So horizontal asymptotes are your horizontal things. So does this have a horizontal asymptote on this graph? Let me pull this back. Sorry, I got rid of it too quick. Does that have a horizontal asymptote? Does it have a line that goes horizontally that they get close to forever and never touch? Yes, what would that line be? Not x, x is this way. Y equals 0, right? So we see that? Does this one have a horizontal axis? Yep. And so horizontal asymptote is just we're going to have one horizontal. You could also have them like this, where the graph gets close to it but never touches it on an angle too. That's a slant asymptote, okay? And so that's what we're going to be looking at and talking about right now. Let's do the rules here. So for horizontal or for slant asymptotes, the following rules apply. We're going to give you the rules first, then we're going to play with some of the examples, okay? If you have one that looks somewhat like this, okay? And this is just a general one. If you have a function that looks like this, there will be a horizontal asymptote if the numerator, degree is the exponent, right? So what's the degree of this one? What's the degree of the numerator? Yeah, good, 1. What's the degree of the denominator? So if the numerator degree is smaller than the denominator degree, okay, then you will always have a horizontal asymptote. Is everyone okay with HA? You'll have a horizontal asymptote at y equals 0. Okay? And is that true over here? Where was our horizontal asymptote? Look at the degree. I had an x, I had an x squared. Which one's a bigger degree? The denominator. So the numerator was smaller than the denominator. And where's my horizontal asymptote? 0. So everybody see that? And so that's always 0 if that's smaller. Okay? So all you have to do is look at degrees and you know it's like, oh, y equals 0. That's an easy one. It's smaller. So that's the first type. The second one is what happens if they are not the smaller. What if it's equal? What if I had like x squared plus 1 over x squared plus 2x plus 1? Where would the horizontal asymptote be now? Well, you have to do this rule. If the numerator, degree, is equal to the denominator degree, right? Then you have to take, and I'm going to add a couple of numbers here now, okay? Let's add 3 and 5. You have to take the coefficients of your highest degrees, your lead coefficient, right? So I'm going to label the lead coefficient like this. I'm going to put the lead coefficient is A of your numerator divided by the lead coefficient of your denominator. So everybody see that? Lead coefficient is what A represents. A is your lead coefficient. So your lead coefficient divided by your lead coefficient is going to be your horizontal asymptote. And so your horizontal asymptote will be equal to, in this case, the horizontal asymptote would be what? 3 divided by 5. And you just set it equal to y, and that's your horizontal asymptote. And so that's 3/5, right? So it's not even a full 1 unit up. Most of the ones we'll have you do are going to come out to be whole numbers, but you could get fractions there, and it's okay. All right? So that's the second rule. You guys got to guess what the third rule is? Let's see here. Maddie, what do you think? What do you think the third rule is probably going to refer to? We've got, or sorry, not Maddie, Madison. We've got this one where the numerator is smaller. This one where the numerator is equal to. So what do you think the third one's going to be?
When it's bigger.
When it's bigger. There's actually 2 cases when it's bigger though, so we're just going to do the first case, okay? So if the numerator degree is 1 bigger, key is 1, right? Is 1 larger degree, I'm going to write that differently, is bigger by 1, than the denominator, then we have what's called a slant asymptote. So I'm going to put this in color here so you can see it. then we say it's a slant asymptote. Okay, it's no longer horizontal. Once you cross that equal sign, the horizontal is not there. It's going to be a slant asymptote, meaning it's going to be on an angle, okay? And so in order to find this is the third here. I'm going to do this option here. This option is going to be a slant asymptote. So if we do this one, let's do f of x equals, let's just make it simple, x plus 1 over, or sorry, x squared plus 1 over x. And that's not going to be a good one. Let me go get my example I had. I can't remember it off the top of my head, so let me grab it real quick, okay? I forgot the. All right, so if we want the slant asymptote, and I gotta find it. I did good at remembering all the other ones, so. Let's do this one, x cubed plus 2x squared plus 4 over 2x squared plus 1. So x cubed plus 2x squared plus 1 over 2x cubed plus 1. That actually was a 4, sorry about that. 2x squared plus 1. Make sure I got this correct here. Yeah, there we go. I got it right now. So because the degree is larger on the numerator than the denominator, we know there's no horizontal asymptotes, right? But it is a slant asymptote. And so we're going to go ahead, because it's only a difference of 1, right? So we're going to go ahead and we're going to find the slant asymptote now. This one takes a little bit more math, a little more algebra. We have to do the division. See how this is a division problem here? The fraction is division, right? You have to divide it to find the slant asymptote. So let's go ahead and divide this. So let's go 2x squared plus 0x plus 1. And we're going to divide it by, or divide into, x cubed plus 0x squared plus 2x plus 4. And we go ahead and walk through this division problem. So what do I need to multiply it first to get to x cubed? 2x, give them a piece. And we multiply that through. Be careful with your negatives. Some of you struggle with that sometimes, right? And plus 2x. And then what do we do next? What do we do next? What's that? Minus everything? Did I multiply through correct? Oh, it's a 4. I put 1 again. That's a 1. What should be 4? 2 times 2 is 4. Let's see here. We don't need to multiply by 2 then. What do we need to multiply by? Just an x. That's better. X times 2x squared is? Well, will an x make it match? Oh, we're going to have to do a half x, aren't we?
Are you serious?
That's okay. It's easy, okay? 1 half times 2x is what? Now we get an x cubed. There we go. That's working out better. The nice part is 1 half times 0 is still what? 1 half. And what's 1 half times 1? Oh, that's going to be a 1 half x2. So, Mike, you can handle the timesing by 1 half though. Come on, Kyler. You got this. All right, and then now that we've got the correct matching here, right, so they actually cancel off, isn't that nice that you can check that? If that doesn't cancel right, you multiplied by the wrong number, right? And then we're going to distribute our negatives through so that we get all those correct. And so that's going to cancel, right? The zeros cancel out? Yep, the zeros are gone. So we bring down this and we get 2 minus 1 half is 3 halves, right? Bring down your 4. And can x squared be turned into an x? No, that's now how we know we stopped, right? And we have our division. There's our quotient, our answer, and our remainder, right? So here is the key. This, right here, is your slant asymptote. So the slant asymptote is at y equals 1 half x. Which is, you guys know how to do that, right? How do you graph y equals 1 half x? Goes through 0. Rise of 1 over 2, right? Rise of 1 over 2, it's just standard slopes. And that is your slant asymptote, okay? It's going to be a pretty quick process. You ignore the remainder, okay? Don't worry about this. This is not part of the asymptote. okay? The asymptote is the y equals 1/2 x, it's just the quotient, okay? So the asymptote is the quotient of the division, and just ignore the remainder, okay? Go ahead and put that in your calculator, would you? X cubed plus 2x plus 4 over 2x squared plus 1. And let's see if we have it. The asymptote should go through 0, 0, and then it should go up 1 over 2, up 1 over 2, right? Perfect. That's great. Does it go towards it right there? See how, if you draw a line there, was it a line at 1/2 x? Okay. And this one is a little bit different, but you'll have that 1/2 x going up on the diagonal, right? You'll have a 1/2 x there. Good? See, it's right on 1/2 x, up 1 over 2, up 1 over 2, up 1 over 2, and it's crossing it, right? So it's getting closer and closer for it. Even though it doesn't have the tails, it's still getting closer to it on the asymptote. Okay? So that looks good. Questions there? All right, so so really what do we look for? What's the most important thing that says find the asymptotes? What's the first thing you look at then? First you check vertical asymptotes, and you look at when is your denominator 0, and you check for holes by factoring and seeing if anything comes out, right? Because you have vertical asymptotes and holes that both could be there. Second is you look for this, go down this table. You look at the degree, and you compare. If it's smaller, it's always y equals 0, no math needed. If it's equal, you have to divide the lead coefficients of the highest exponent, right? And then you can get your y equals the horizontal asymptote there. If it's 1 bigger, then you have to divide the polynomials, and your answer without the remainder is your slant asymptote equation. Okay? And there's one more option. What if it's bigger than 1? What if it's further away and it's not bigger? Well, it's not 1 bigger. What if it's x to the 4th and x squared? What do we do then? The answer is there's no horizontal or vertical asymptotes. Okay? So there is one more step here. I'm kind of running out of space. I'll write it right here. Number 4. If you have something like this where it's x to the 5th over x cubed plus 2x, whatever, it doesn't matter what it is, the numerator degree, right, is bigger than the denominator degree. Yeah, we'll say the denominator degree. Okay? Then what's true? And it's not bigger by 1. If it's by more than 1, then what do we do? There are no, don't say no asymptotes, because there still could be vertical asymptotes, or verticals, right? No horizontal asymptotes, and no slant asymptotes. Okay? Is there horizontal asymptotes when it's bigger here? What do you guys think? Does this one have horizontal asymptotes? Number 3, if the numerator degree is bigger by 1 than the denominator degree, is there a horizontal asymptote? The answer is no. What is it called? So your assignment is split into horizontal asymptotes on day 1, slant asymptotes on day 2. Okay? And so tomorrow we'll have homework on that more. But today, I wanted you to see the whole picture. Okay? If it's a slant asymptote, then there's no horizontal asymptotes at that point. Okay? And vertical asymptotes are on all of them, or can be on all of them. You actually have to do the math though. Set the denominator equal to 0 and solve it. There are times when there are no vertical asymptotes because they can never go to 0. Okay? And so we will go to there. Any questions at all? Sweet. You got about 20 minutes to work on homework, and then tomorrow we'll review this and we'll go over any questions and you'll practice it again, and then Friday we'll just kind of finish up, and we're actually finished with the chapter, so we're going to start wrapping up and reviewing and getting ready for our test. Most likely will be Tuesday. Okay? And then we will start chapter 3 next week, and go into our logarithms, okay? Yes, you may. Okay, I'll come around and help you guys.